Welcome to this session on augmented reality at Mention Computer 2020. I'm glad that you joined the session. And before we look into 7 very interesting papers, let us just first introduce myself and also soon my co-chair. My name is Susanne Boll. I am leading the research group Media Informatics and Multimedia Systems at the University of Oldenburg. I have been attending Mention Computer many years, and I enjoyed it to grow, and I'm really happy to see such exciting papers today, and I'm happy to chair the session.
Yeah, hello, and my name is Christian Hansen. I'm leading the Virtual and Augmented Reality group at University of Magdeburg. Yeah, I'm really excited to announce the first talk for today. So the talks were submitted via video beforehand. The first paper has the title Effects of Position of Real-Time Translation on AR Classes. It comes from the University of Regensburg, and the first author is Rufat Racek. So please start the video.
Hello, my name is Rufat Racek. I am presenting the work titled Effects of Position of Real-Time Translation on AR Glasses. Augmented reality is advantageous for learning use cases, as it can display the explicit relationship of virtual information and real-world objects in the user's environment. For example, augmented reality can be used for the real-time translation by overlaying the text in the foreign language in the environment to learn unknown words. Some research-related and commercial real-time translation AR applications for smartphones, such as Translate AR or Google Translate, overlay foreign words with translations. In these cases, the real-world information is hidden from the user on the smartphone screen. However, using the same concept on the AR glasses will completely hide the real-world text from the user. A user might be interested in not only the translations, but also the learning of the foreign words. So it's not clear how the position of real-time translations using AR smart glasses support the learning experience. For this purpose, we conducted a study and we implemented a HoloLens application that recognizes predefined Finnish words and displays their translation in German. We use the Finnish language since it belongs to a different language family than the German. The application enables to switch on and off the translation using the HoloLens clicker. The application can display translation in 3 positions: overlay, as in mobile Google Translate application, right and below the foreign word. Right and below positions were selected due to the reading direction in the country of the study. We employed the repeat measures design with position as an independent variable with the levels overlay, right and below. Position was counterbalanced across all participants. Through the study, we measured comprehension, the learning time, subjective task load using the raw TLS questionnaire, usability using the system usability scale, and participants provided subjective feedback. During the study, participants were sitting in front of the TV where the Finnish words were displayed one by one. We used the TV to be able to switch between the words and randomize their order during the study easily. This setting allowed to study a mobile AR translation scenario where usually a word or short phrase is needed to translate. We asked the participants to imagine being on vacation in Finland and using the HoloLens application to learn unknown words that they encounter. Per condition, participants learned 10 unfamiliar words. After each learning session using the translation position, participants filled out questionnaires and did a comprehension test. Finally, participants provided feedback about each condition. The results showed that the comprehension score was significantly lower for the overlay position compared to the below one. There was no statistically significant difference for the learning time. This shows that participants spent similar amount of time to learn words in each condition. Overlay position resulted in significantly higher subjective task load compared to the right position. Compared to usability scores, overlay position resulted in lower SUS score than the right and below conditions. However, this result wasn't statistically significant. For the summary, overlay position results in the lowest comprehension and the highest task load. Participants indicated that, while displaying the translation as an overlay, it wasn't possible to see the direct connection between the foreign word and the translation of it. Through the study, we learned that overlaying the translation on top of a foreign word on a vocabulary learning task using AR glasses decreased comprehension and increased perceived task load. Participants preferred being able to view a foreign word and its translation simultaneously, as it helps to develop a direct link between them.
Thank you very much for the talk. Nice presentation, nice work. It's possible to ask questions via the YouTube chat, and we will read them here in the session. I might have a first question. What did you think about multimodal input? You used text as an input, but maybe do you also think about icons or pictures to increase the learning ability?
So we thought about that. Actually, there are already works that showing not just like this translation multimodal format will provide more, will facilitate the learning of new words, new vocabulary, and for example, not just showing the text, but also showing text and pictures, or also the audio. It will make it better to learn new words. However, we didn't apply it in this work. We just interested in the position of the text translation.
And why did you select the left position and the lower position? I mean, there are more than these two positions possible. How did you make this decision?
The position was selected due to the reading direction in Germany. So since the study was conducted in Germany, to the left to right and down to up to down. And of course, it was possible to select also the left position or up position to translate for the translation words. However, there also effect of there's a work that I forgot the title of this work that showed that there is actually the effect of order, how you learn the language. Like if you learn from the first the foreign language first, you said the word in first and foreign language, and then on your own language or the other way. So adding more this positions will also add this like bias of the order of learning. So will add more say more conditions, or also deal with the confounding bias. So we just use just these two. But overall, it's interesting to know if there's any effect of learning the order of learning words on the position, and also on the effect of the learning new vocabulary.
Okay, I see we have one question in the YouTube chat. The question is, what was the reasoning for selecting the different positions? How about investigating
other
positionings?
So it's kind of similar question, right?
Yeah.
So as I already answered, yeah.
My follow-up question would be, is the optimal position maybe depending on the task? So for example, if you walk left, you expect also the label on the left hand side? So is it task dependent?
Yes, it's task dependent. Like since the study was conducted in Germany, the reading direction is to left to right, so that's why like this position was selected. But in different cultures where there's a reading direction is to right to left, will be probably better to place it in like in the kind of study use this left direction, for example, instead of the right.
Okay.
As a question, in addition, I think in your study you said that there was a pretty high workload for the wearer of the glasses. So my question would be also towards the kind of even motion sickness. So how much was this stressful? And what do you think would be the next step to reduce that and to make it a little bit more comfortable? I think, as you said, the positioning was a question, and also the general visual appearance.
The work was more in the overlay position, since the person needed to switch on off all the time to learn to see the original word in foreign language and then see the translation. However, as a condition where it was possible to see the both words simultaneously, the workload was less. And like in general, since we use the whole lens, it's bulky, it's heavy. So it's almost in all studies, participants indicate that it's heavy to wear it for a long time.
Yeah, I think someone even said that, or asked in the chat, would you expect different outcomes using different hardware, so other than HoloLens? So that probably relates to what you just said. So what would you expect then?
Probably regarding the workload, regarding the positions will be probably the same, since it's since they were wearing the same device in all these conditions. But I can guess that probably the workload in general, like people will not feel that wearing something very heavy, and like in normal case, people will not want to wear a HoloLens for a long time.
Yeah.
But with
exactly.
Yeah.
Thank you.
Okay. Thanks. Then I think we can come to the next paper, huh? Susanne?
Yes. So thanks again for the first presentation and question answering. So we are moving on to the next paper. So Mind the Arm. So it is about real-time visualization of robot motion intent. And Uwe Grünevold is presenting on behalf of also his co-authors from the Office Institute for Information Technology.
Welcome to our paper presentation of Mind the Arm, real-time visualization of robot motion intent in head-mounted augmented reality. My name is Uwe Grünevold and I'm from the University of Duisburg-Essen, and I present this work on behalf of my co-authors from the Office Institute for Information Technology Oldenburg, Lars Brede, Jannike Illing, Tim Stratmann, Sandra Drolshagen, and Max Pfingsthorn. If we take a look at state-of-the-art industrial robots, we can see that their safety systems are reactive. This means that industrial robots shut down if a human operator blocks the motion of the robot arm. Triggering this robot shutdown is problematic because it results in a halt of production and hence a loss of productivity. Therefore, in our work, we aim to visualize the robot motion intent for human operators, empowering them to avoid robot shutdowns due to close proximity. We implemented 3 visualizations in Unity 3D for the Microsoft HoloLens: Path, Preview, and Volume. For all visualizations, we used the color gradient from blue to red to encode how close the robot arm is relative to the user. Here, red stands for very close and blue for far away. We base this on the warm and cold metaphor used, for example, in heat maps. The path visualization displays the path of the robot arm as a line. This path shows the future positions of the robot's end effector only. An advantage of this visualization is its simplicity, though by neglecting other parts of the robot, the visualization is not complete. The preview visualization shows the full robot configuration by rendering robot meshes at the interpolated waypoints. Compared to the path visualization, this visualization has the advantage of showing all degrees of freedom of the robot arm. The volume visualization is based on a cylinder around the robot, which is cut into slices along the radial axis from the center line. The volume slices that the robot will occupy are visualized using the color gradient from blue to red, while empty, safe slices are colored green. For the evaluation, we designed a within-subject laboratory user study with a small cognitive task carried out by the participants. Our independent variable was visualization with 3 levels: pass, preview, and volume. And we had the following dependent variables: robot angle on leaf, head pose in robot area, task performance, workload, and subjective measures. Overall, we had 18 participants, of which 5 were female. Our participants rated their experience with augmented reality between low and medium. In our results, we found significant differences between all conditions for the median head rotations. Here, volume resulted in the lowest average head rotations, while pass resulted in the highest average head rotations, indicating that more head movement was necessary to understand the robot motion. Furthermore, we found significant differences between preview and volume for robot angle to participant on leaf. Here, volume allowed the robot to come much closer before participants were leaving the robot working area. In summary, we can conclude that all participants managed to exit the robot working area before collision could occur. Participants rotated their head more towards the robot arm for path and preview, while volume required significantly less head movement. Furthermore, volume was rated most reliable by participants. In general, we could show that head-mounted augmented reality is suitable to show robot motion intent. For more details of our work, please have a look at our paper. Thank you very much for your attention and enjoy the conference.
Yeah, thanks, Uwe, for this interesting insight into your work of cooperating with robot. We have time for question answering, and I would like to answer. I think the initial question was that if you are halting a cobot, it would cause maybe potentially a large amount of cost for the production line. Would you anticipate that this system is actually kind of patronizing the workers? So the robot goes first, and then the robot decides where to go and where the human should not be. And if it's, I like this kind of question. So is there, it's a failure by the human if the robot has to stop. So what is considered to be a safety feature could be turned into a question of why didn't you dare go into the red area and make the system halt? Did you already have experiences in what it means for a human machine or human robot collaboration?
Yeah, thank you first of all for the question. So yeah, I think we have to look at it from like a historic perspective of like where are we coming from, right? So like in the beginning, we had like these robots that were like hold behind like safety cages and nobody should come close. Then we switched a little bit over to like these safety constructs where they can kind of recognize that somebody enters the area and the robot stops. And I think this is just the next logical step kind of to help the human to understand what the robot is doing, especially when given current times, like AI makes things more complicated, less predictable. So I think that's a very good first step to kind of like say, hey, the robot like tells you what it's planning to do and you can consider it. But definitely we're not done with the research here. And in the future, there's more research required to really make it a collaboration, not kind of a, I tell you what you have to do and you have to react kind of.
Yeah, thank you. We also have a question from the audience. So the question was that it seems that you are showing that only one joint is active at the time. So did you visualize the path also when the robot is moving into all directions?
Yeah, that's a very good question. So yeah, we tried out different things in the beginning, and also we're looking in like different robot motions. But yeah, as a starting point, we narrowed it down to like kind of say, okay, what's most important for the position of the person is kind of when the robot like really moves in space, so to speak. And yeah, that's kind of why we were investigating this first. But definitely, this is something that we should consider for the future, especially since some of the visualizations that we showed, like the past visualization, for example, has not really a good ability of like showing where like the parts of the robot are. It just shows like where the end effector is and is going to be. Like kind of like tells you a little bit less about like what the robot arm will look like. So I think but we have like some insights already in that direction, so that something like the preview visualization might be like benefiting from like different kinds of motion more than it does here.
Okay, thank you. And there's another question. It looks like the volume method occupied a lot of the visual space.
Mm-hmm.
So was it a problem for the participants?
Yeah, so we had like this little task that participants were performing, right? So we had like a kind of like a math puzzle where we showed like equations, and participants were just asked to kind of like say if they're true or not while they were kind of standing in the robot area. Yeah, and we found here like that there were no differences in performance. So we saw that even though we kind of occupied with the volume visualization a lot of visual space, it did not like impact it at least significantly. At least we didn't find a significant effect here. And I have to say, like in the video a little bit, so it's kind of hard to show what the user really perceives when like having the HoloLens. When wearing the HoloLens, and in this case, like the volume, it looks like it's really over the place, but there's actually like occlusion going on. So like the display was occluded out of like the volume visualization, as was the robot arm. Just the HoloLens has not the capability of recording this occlusion.
Oh, okay.
Looks worse, so to say.
Good.
Do you think it's also possible to visualize these things you present with a projector-based augmented reality setup? Because most of the previous work that I see in human-robot interaction uses projectors. Mm-hmm. So do you think this is possible?
Definitely. That's an option. What inspired our work was a previous work by Rosen et al., where they compared different technologies. So like desktop-based versus projection versus head-mounted, and they found that head-mounted actually was perceived best by participants. So that's kind of why we made this choice to go with like the head-mounted. And also projection has always like the disadvantage that it needs a surface to project onto, right? So, and this kind of is not clear for every robot working environment that this surface is really there. And so it has a huge impact also from my perspective on how people perceive the visualization. So therefore we chose like the head-mounted version here.
I don't see any more questions in the YouTube chat. So I think we can proceed with the next presentation.
Yeah. Thank you, Uwe.
Thank you. Yeah. I just closed my list here. No, I haven't. So the next talk is from Technical University Clausthal. Nicolas Karl will present a paper about Show Me Your Living Room, investigating the role of representing user environments in AR remote consultations.
In this video, I want to give you a short overlook of our paper, Show Me Your Living Room, investigating the role of representing user environments in AR remote consultations. Buying furniture is a difficult matter when today's furniture offers hundreds of different choices. In furniture stores, consulting helps to adjust the object to the respective requirements. But what about consulting from a distance? What if you could see the furniture on your own four walls? With augmented reality, remote consultation offers such a possibility. To see the furniture on the spot where it should stand later on, cutting time and traveling cost for the consultant are just some of the benefits. With video streams being an often used solution, recent approaches used some form of virtual environment to enhance spatial understanding and immersion. Keeping that in mind, we wanted to know which type of representation works best for consultation. We created a study investigating AR-based support for remote consultation and conducted it with 9 experienced furniture consultants. We used 4 different scenarios where an actor was interested in a new furniture for their living room. The actor was at our facility in our living room lab, while the consultant was at the furniture store in a closed office. In each scenario, the customer had different needs and wanted to buy a new couch, while the tools provided the consultant with 9 different furnitures. For the study, we tested the 4 following mechanisms. 2D video, where the consultant's view was the same as the customer's and interaction was realized directly in the video stream. 2D display fixed view, where the view was fixated as well and the scene was pre-captured and texturized with the Microsoft HoloLens. 2D display free view, where the consultant could move freely and interact in the pre-captured scene. In the unrestricted view scenarios, the consultant could see the view direction of the customer. And VR HMD, with a pre-captured scene and the full VR possibilities. For the evaluation we used raw TLX, part of the Network Minds social presence inventory, custom questions, and an interview right after finishing the last experiment condition. While the questionnaires showed no significant differences, we are able to see tendencies towards VR being more demanding. Even when the questionnaires showed no significant differences, interviews indicated that consultants liked the virtual representation better. They preferred Freeview and VR. While VR was at the same level as Freeview, it might provide additional positive effects with more training, as participants stated that they would need more time to familiarize with VR and that this could lower the distraction they perceived. 6 of the 9 participants stated that the capture view would already be a helpful extension to a furniture consultation, and that they could imagine working with VR under certain conditions, such as a longer familiarization phase. While the VR result showed promises, they need further research to ensure that the familiarization would have the wanted effect. From our data with furniture consultants, we recommend a combination between a 2D Freeview and a 2D fixed view application, where the user can choose freely between these states. Either way, we would discourage the mix between VR and 2D, as it would interrupt the flow of the consultation. Thank you for your interest, and for further information, please refer to our paper.
Yeah, thanks, Nicolas, for the talk. I think I wait for some video questions, but before the first question comes, I have one question. So I'm interested if you find real customers for your study or for your requirement analysis. I understood that you mainly analyzed the consultants.
Yeah, for this study we used one of our workers, and he played the part of the customer so that we have always the same setup and don't get additional variables. Okay. For sure, it's interesting, and it could also generate further knowledge with real customers, because there's always, if you want to buy, explicitly want to buy the couch in the scenario, you probably would have some more details you want to know. So this could have an impact, yeah.
Okay.
There's a question in the YouTube channel from on the question of this, very much relating to what Christian just asked, is so furniture sales personnel is probably not familiar with suggesting interior design. So did you think about using interior architects as a user?
So specifically in this scenario, the study was under the banner of the RBAE project, and that is a project where we want to focus a consultation between a customer and the furniture reseller. So in this scenario, we focused on the furniture reseller or the consultant.
Yeah, but probably I think Jürgen Ziegler's question goes into the direction that an interior architect might also have a good sense of style, you know, sort of saying maybe better than just selling you the couch.
For sure. I mean,
it's like a good, let's say, golden ratio or so. That probably was the intent of the question.
It could also work for interior designer for sure. If you have the picture of the room and if you can actually see how the room is looking, that could be also applied to that. Yeah.
I personally like this IKEA augmented reality app. I use it a lot when I move my apartment. So this is without consultant. So my question is, how did you define which interaction methods and visualization methods should the consultant have? So did you use previous existing apps and interviewed consultants and customers? Or how did you define the interaction and visualization possibilities you designed?
Okay. Yeah. So first of all, we looked about or on previous work and collaboration. Of course, buying something is different than other collaboration, but in the core, it's still the same interaction. So like looking at places or pointing out specific details is still the same in the setup. Yeah, so we looked at previous work. We knew that we would work with the HoloLens, and under these conditions, we then decided which conditions would be feasible and could have an impact. Yeah.
Thank you.
And maybe as a final question, if I may, just the question on the realism. You know, I'm sure this much plays a role. You know, how realistic does this, whatever, 2,000 euro couch actually is? How realistic is it mapping into the lighting? How does it look when I watch TV? And so did you get anything like, I know it's a first study, I'm well aware of that, but sort of maybe you have some insights in how close you still have to come for a more realistic decision if you want to buy not only a certain couch, but maybe also in a certain fabric and in a certain color.
Yeah, for sure. Okay, so the data we used was actually data from the furniture companies. So this is pretty much the best you could get from if you consider the furniture. Then again, like the hugest impact would have for the representation, at least for the client, would be the limitations from the HoloLens. So in that regard, you will always have or from other headsets for sure, but you would always have these limitations. It could be improved by a lot still if you consider things like normal mapping and other computer graphics topics, but overall it's already on a good point where you can actually really see how it would look like in your living room.
Thank you.
You're welcome.
So I guess this concludes this question and answering session. Thanks again, and we thank Nicolas for presenting it. And we could go over to the next presentation. Clemens Hoffmann is presenting joint work from Volkswagen, from Clausthal University of Technology and Ostfalia University of Technology. And we want to hear about the impact of augmented reality guidance for car repairs on novice users. So maybe everything for all of us, and see how the field experiment worked. So we hear the presentation first.
Hello everybody, my name is Clemens Hoffmann and I warmly welcome you to my presentation. I will give you a short overview about my last AR study. For further details, check the full paper, please. In 2017, there were around 80 million car workshop orders in Germany. We are researching for a new way to support the service technicians at these orders. We focus on service technicians who work at their workplace under field conditions and had no experience with AR. Our experiment integrated two sub-studies related to different levels of task familiarity. The familiar task was to replace the car front bumper. The unfamiliar task was to replace the front wiper motor. The procedure started for all participants with an introduction. Afterwards, every participant executed one of the tasks with a traditional repair guidance. For the second task, the participants got an AR introduction based on the already executed task. Then they executed the other task with the AR guidance. In a short interview, at the end, the participants were able to give us feedback to the AR application. On the left side is an example of the traditional repair guidance. The repairs are described in written form with 2D graphics. On the right side is an example of the AR guidance. The written information are in a movable text field. We use the model tracking to project the 3D animations over the real vehicle. On the next slides, I will present our results of the study. For explanation, AR means Augmented Reality Group and TRG means Traditional Repair Guidance Group. We measured the total task completion time, the assembly time, the support time for retrieving information, the tracking time for recalibrating the AR HMD after up or down lifting the car, and the net time is the total completion time under the assumption that no recalibration of the AR device is necessary. For the familiar bumper task, the AR group was in total 40 minutes slower than the TRG group. The AR group needed twice the time for retrieving information. Also, the net time showed significant differences. We counted the number of wrong orders, missing and unnecessary steps, the total amount of deviations and the deviations that affected the final quality of the repaired component. The most deviations were altered sequences. There were no deviations with quality impact. We discovered three interesting findings from the first sub-study. First, the novelty of AR support slowed the service technicians down. They needed time to get used to the application and the control. Second, the participants followed not exactly the introduction of either support medium. The routine with the familiar task had a strong impact on the results. And third, all participants discovered process or task efficiency optimizations within this task. For the unfamiliar task, we had no tracking time because the car was not lifted. The total and the assembly time showed positive tendency to the AR support. The TRG group needed less time for retrieving informations. The AR group performed 74% less deviations compared to the TRG group. The differences in deviations with quality impact is even bigger. For the unfamiliar task, we have two interesting findings. First, even with the effect of novelty to AR and some controlling issues, the AR group was not slower than the TRG group. Second, the AR support had a positive impact on the quality. The AR group followed step by step the introduction and did less deviations. Our study revealed following conclusions. The AR support has a negative impact on the time for a familiar task, but with the effect of novelty, routine and task efficiency optimizations, we cannot give the AR support a specific disadvantage or advantage. For the unfamiliar task, the AR support has clear advantages. The AR support has a positive impact on the deviations for unfamiliar tasks. Our opinion is that an AR HMD repair guidance provides immediately support for unfamiliar tasks and can accelerate completion times when the service technicians have more experience with the support medium. Thank you for your attention. I'm looking forward to your questions and feedback to our study.
Yeah, thank you very much for these insights into the future of repairing a car. That was very interesting. I would like to start with the familiar task. I think that was clear that it was not maybe so supportive as you might have maybe hoped. The question for me would be, is it even worse if you would use it again and again? One thing you said, it was difficult for those who were not familiar with augmented reality. On the other hand, if you would run the same experiment like a few weeks after, like regularly again, and you would have time for that, do you think it would be a better support, or it would be even worse that people say this is slowing me down?
I think, yes, it will get better, but the traditional repair guidance is like you can just choose what you want to read, like, and then when you have a lot of routine, you just check like some small details and you know just what you have to do. So, and the repair guidance was really, AR repair guidance was a step-by-step guidance. So it was not so easy to overstep something. So we have to change the AR application a bit. That is maybe also like bigger overview for everybody, that they not have to read everything and to do everything step by step. So I think it would be possible, but
and in line with that, it's the question, you know, is it for a familiar task good to have it in place, or would it also be something where you say I'm kind of often doing this and that, and then AR gives me a quick refresh of the next steps, like a quick highlight of what exactly this car has a specialty in, rather than this continuous guidance?
I think that is possible, like that just giving the service technicians just a short overview. We have also like in the beginning, like always an overview about the whole task, like some explosion of the repair steps. So maybe they can just work with it, but Volkswagen is also interested in, of course, that they do it like in the right way and not do it like how they think they have to do it. So it's always also important that we give them like some kind of guidance and not let them just do it.
And for me, a natural thing, you said that the other task was an unfamiliar task. I thought also it would be a good training tool for maybe apprentices or people who haven't done it before. Did you also consider it more as a training tool? If you, let's say, if there's a new brand out and it has maybe a complicated part or something that is difficult to change or repair, did you think that could be also beneficial?
Yes, that's exactly what we are doing now. Like this week, we start with the next study and we're exactly doing this, having a new task at a new car, what nobody knows. And it's really like some kind of training. And we also doing the repair 3 times so that we see after 2 weeks again if there's some changing with the technology. So yeah, we think that's like also like maybe better way for like training and getting first repairs, so that the technicians get direct a very good overview about the repair task and do it direct at the first time, everything right. So that's what we're hoping.
Okay, and if I just conclude, the question is for me also, do you think of tracking mechanisms? I think there's a lot of research also going on in observing the human and to see when do you need a support and when not. I think there's other research group on human modeling, cognitive psychology to understand if I understood it or if I'm irritated. Is that something you also plan to do?
No, it's not part of my work. Like I read about this, and we had also some other PhD guys in Volkswagen who are really doing like this tracking. So yeah, I hope maybe in some years this combination of our works will come together, and then we have like this tracking of the task, what is like exactly the problem now, and when the participants need help. Yeah.
Okay, and I think I've overlooked questions
in the YouTube chat, yeah.
Oh yeah, Chris, do you want to follow up on these?
Yeah, I can just read the questions here from the YouTube chat. So Mark Herrlich is asking, should we now use augmented reality mostly to teach new tasks and then stop using it after learning the task? Is this something you recommend?
That is what I'm now looking at. Like I really look at this now, like doing the task 3 times with AR and then 3 times with other group, do 3 times with the traditional repair guidance. So maybe in half a year, I can write a paper about this and can give you more details about it. At the moment, I would not say, like I can't give like clear answer to this question.
Entros Ecke is asking, the procedure of a familiar task should be well known to the user. Why should you provide further assistance in that task? This is maybe some critical question.
Yeah, we just wanted to know if we can use AR generally in the garage, or if we have to decide in the beginning, we just do it for new tasks, but in the end, there's also maybe some guy knowing the task and want to use also is AR. So we don't want to have in maybe 10 years 2 different kinds of guidance. We want to have like maybe just AR, but we will see.
The last question from the YouTube chat is from Jürgen Ziegler. Also some comment or maybe question. Describing the repair procedure only textually in a scrolling window might not be optimal AR use. Have you thought about breaking down the procedure into steps and locating them next to different parts?
Yes, it's exactly what is already doing the application. It's like some animations over the real vehicle and also text information, like combination of both. But there's for every step an animation, what the participants has to do.
Okay, thanks. That's all from the YouTube chat. Okay, I think then thanks a lot for answering all our questions and for the nice presentation.
Thank you.
And then I
have a nice day.
Switch to the next talk. It's from Sebastian Büttner, augmented reality training for industrial assembly work. Are projection-based AR-assisted systems appropriate?
Welcome to my talk, Augmented Reality Training for Industrial Assembly Work. In this talk, I will address the question, are projection-based AR-assistive systems an appropriate tool for assembly training? My name is Sebastian Büttner, and I carried out this work together with Michael Briller and Carsten Röcker. In this talk, I present a study on training with AR-assistive systems. The goal of this work was to learn about the training efficiency and the knowledge sustainability of these systems. In our study, we compared projection-based AR training with 2 control groups: a personal training as an optimal case and self-learning with technical documentation as a low-cost case. Before I present the details of the study, I would like to show you what a projection-based AR assistive system actually is. Here you can see a user with the assistive system in action. Basically, the system shows the user how to assemble a specific product. Here we see information about mounting points and the location of parts. Additionally, videos or 3D drawings can be projected into the work area. Now the participant made an error, so the system makes the user aware of the error. When the error is fixed, the participant can continue the assembly process. So the setup of our study is shown in this image. This setup was used for all 3 conditions. You can see an assembly workplace which is similar to those that you can find in industry. It basically consists of a table and some grab containers for the required parts. Above the table is a projector for the in-situ projections. Our study followed a between-subject design with groups for the 3 different training conditions. 24 participants completed the study. In the first training session, we let the participants execute the assembly task repeatedly under the training condition, until they could execute it without help. After 24 hours, we let the participants execute the assembly task without help to find out how well they remembered the task. If participants made any errors, we continued with the second training session. We evaluated the knowledge of the participants 6 days after the second training session by executing the task and by answering a multiple-choice test. Now our results of the study. First, we look into the training efficiency. To the left, you can see the number of training cycles. To the right, the total training time in minutes. One interesting finding is that we did not have any significant differences between the groups on the first training day. However, on the second training day, the participants of the personal training group needed much fewer training cycles compared to the other groups. It seems as if the personal training group had a more comprehensive understanding of the task after the first training day. There were no differences between the AR condition and the paper condition. However, I have to add that we excluded 2 participants from the paper group that systematically learned the task in an incorrect way. This was only possible in the paper group, since participants in that group did not receive any feedback. If we hadn't excluded these 2 datasets, the paper condition would have resulted in worse training efficiency. So we can clearly say that AR assistive systems prevent the systematical learning of incorrect work steps, which indirectly leads to better learning efficiency. When we look into the data of the knowledge sustainability, we can see a significant difference of errors between the personal training group and the other two groups after 24 hours. However, when we look into the number of errors when executing the task after 1 week, there are no significant differences between the groups. The same holds true for the quiz results. The participants answered about 20 out of 25 questions correctly, regardless of the group. So our study showed that once the task was learned, the knowledge persisted in the same way, independent from the learning condition. So to conclude my talk, our study showed that a personal training had the best training efficiency. Our observation showed that AR training successfully prevented systematic incorrect learning. However, other advantages of AR could not be proven. We found that the knowledge sustainability is independent from the training condition under which the task was learned. Thanks for listening to our talk. If you have any questions or comments, please get in touch with us.
Thanks, Sebastian, for this talk. Yeah, we're waiting for YouTube questions, but maybe I can start with the first question. It seems that the personal training is quite good. Yeah, maybe hard to beat. Do you know which parts of the personal training have a high impact on the training efficiency? Is it the motivation that the trainer gives, or what is the secret?
Well, the results are exactly what we expected in terms of personal training. I mean, it's obvious that it's the best option if someone's sitting close by and can adapt to the current behavior of the one that needs to or that is trained. I cannot answer this question based on the data that we presented in the paper. However, we recorded all the sessions on video, and what we are currently doing is that we want to watch all videos, especially the ones from the personal training, and look for, let's say, verbal or non-verbal behaviors that maybe could bring some benefits to the user that learned the task. So this is kind of something for future work that we want to address. We want to look into how this personal training works and which aspects we can use and maybe use in a very intelligent adaptive assistive system that kind of can adapt more to the user than the current state of the systems can. So we think that we might be able to do this more adaptive and learn from this personal situation.
So how intelligent was your system, your AR system? I mean, of course, you had an intelligent personal trainer and he adapted, but how intelligent was your system? Can you comment this or explain this?
Well, I must state it was not very intelligent. So we had different levels. We had 4 different levels of information, and the users in the study, they could select the current level. So they started with a lot of information, and when they felt comfortable, they could reduce the amount of information. In the personal situation, we had a similar setup. So the users were asked how much information they want to have. So they could always give feedback to the trainer and said, I need more information, or I need less information. And the same was true for the system, but the system only had this specific 4 levels of information. And what we always had in the system was that we gave feedback when something was wrong. So this was a Wizard of Oz approach. So whenever some error occurred, information about the error was given to the participants in the AR condition.
Thank you. Now it's clear for me.
Were you actually hoping that the AR condition would be better remembered?
Well, I didn't expect that it was better remembered in the compared to the personal situation, but I hope that it was better compared to like this paper manual, because the paper manual just had this 2D information, and I thought that maybe this 3D information in the workspace could be better for remembering the task. But yeah, this wasn't true. So
Yeah, but the question is also, people have been used to some paper instructions for a long time. So the question is, of course, how much training would it need that you adapt to that new? I think everybody knows these Lego instruction manuals, and if you are used to that, you can do it pretty quickly. So maybe that was also an effect. Did you test that, and sort of how much of this experience of paper manuals was before? Pretty difficult to check, but that may be a prerequisite that the participants came with.
No, actually, we didn't check it. We asked for it in the recruitment process about the previous experience on. We used Fisher technique in this task, so we asked for Fisher technique, but we didn't analyze it. But I think that's one part of our results, and the other is that all participants they built this model a lot of times. So I think the users do not remember the manual; they remember the process that they actually did. So after 1 week, they don't remember if the manual was printed or if they had in AI instructions. They just remembered what they actually did, and all participants did the same. They built and built and built this model again and again. So that's probably the reason why we had this results.
Right, but it's highly interesting to see that you had results showing that the recall was the same across all. That means it gives also good potential to AR. So that is, I think, on the very positive side.
Yes.
So yeah, thank you.
I don't see questions in the YouTube chat.
No. Then, thank you.
Thank you,
Sebastian.
Thank you.
And then we're moving on back into the house. Thomas Ludwig will be presenting Vacuum Clean AR, augmented reality-based self-explanatory physical artifacts, on behalf of his co-authors from the University of Siegen.
Hi, I'm Thomas Ludwig from the University of Siegen, and I present our paper about our augmented reality-based self-exploratory artifacts that I wrote together with my colleagues Sven Hoffmann, Florian Jasche, and Mario Suhrmann. To get straight into the topic, we need to understand that nowadays most companies operate in globally networked markets. And although global market imply a larger sales market and more customers, they also imply more competition. Due to the multitude of products available, it can be difficult for customers to understand the unique selling proposition and actual innovation of a specific product. This is especially the case for so-called low involvement products that must be clearly distinguished from high involvement products. High involvement products are those products where a customer invests a lot of time searching for information because the product is important to him or her, or the product carries a high risk. Examples are a house or a car. Low involvement products are usually those kinds of products that relate to everyday life and have usually low prices, and the products require little or no justification, such as groceries. Especially for products falling in between high and low involvement, such as hair dryers or vacuum cleaners, the innovations that might differentiate a specific product from the competition can be very hard to spot for potential customers. Current HCI literature already investigates how augmented reality can be applied for supporting product marketing and argumentations with potential customers. And the literature already shows the positive influence of augmented reality on customer satisfaction, and that augmented reality-based images of a product which illustrate its functionalities while entertaining the customers may increase customer satisfaction. In our case study, we explicitly looked at how augmented reality can be used to visualize hidden innovations in an emotional way. To investigate a product that falls between low and high involvement and the impact of augmented reality, we conducted an empirical study within a company that sells vacuum cleaners. First, we had to understand the hidden innovations of vacuum cleaners and how the company sell them to their customers, which is why we work very closely together with sales consultants that are on-site resale stores few days a month and promote the specific vacuum cleaners. These workshops revealed a lot of design recommendations about how to address the needs of potential customers, such as using pets and small animals as ticket to talks during sales talks, or that is very hard for the sales consultants to show the actual functionality of the physical vacuum cleaners and how they work within an actual practice. On the basis of our findings from literature and the design challenges from the empirical study, we designed and implemented a HoloLens application that should reveal hidden innovations and make them more accessible to potential customers in an emotional way. Since our empirical study showed that pet owners are an important target group and the pet is one of the most important tickets to talk, we used a comic dog which serves as a guide through the different tasks. The first task deals with functions and accessories. The vacuum cleaners offers pet owners the opportunity to remove hair and dust from all kinds of surface. This benefit is illustrated by the 3D representations of the nozzles, which the user can view from all sides to gain additional information. The next task is the most important part of our concept and deals with the actual hidden innovation. Here the two box systems that are usually invisible for users are explained by the dog in more details and the benefits of the box are clarified. The user interacts directly with a representation of the real object. In addition to the 3D representation of the boxes, the cleaning effects are simulated so that the user understands how normal dust is separated from fine dust and therefore see the actual unique selling proposition. In the third task, the engine is visualized to illustrate the performance. A virtual engine drives out of the vacuum cleaner with the help of an animation. In addition to the presentation of the engine, the performance is accompanied by spatial sounds and some performance indicators that reflect the vacuuming power. And the fourth task visualized the logo of the company. We then conducted two evaluations to examine the impacts on the sales process. The first evaluation focused on the consultants of the company who are responsible for sales in retail stores, and the second one focused on actual customers. We want to uncover how they cope with AR applications and how they perceive the innovativeness and benefits of vacuum cleaners. Sales consultants in particular are currently critical towards the technology and said that strong human relationships are the key to sales. And such interpersonal relationships are currently lacking, so the application can only be a ticket to talk as an entry point into a deep conversation. The potential end users of our application see the added value of the application in order to better understand the actual innovations. But here too, there was the opinion that it will never replace a technical discussion in person. Therefore, the augmented reality application is rather intended to support personal sales conversations. To conclude, we can say that the huge variety of available products make it challenging for customers to understand the innovations of a specific product, and augmented reality offers potentials in the field of marketing. With our design case study around the augmented reality application vacuum cleaner, we have uncovered some of these potentials, but also current challenges in the use of augmented reality for promoting self-exploratory physical artifacts. You can find details within our paper. I would like to thank the company Robert Thomas for supporting our research. Thank you.
Thank you very much. A very nice insight into augmented reality for future vacuum cleaners. Again, while we are also waiting for questions from the audience, I would like to start still with a question of usability of everything of this. I think there were four buttons that I could more or less select, and I would see different elements of that, and then there was text reading and stuff like that. So what was your approach towards selecting, acknowledging, and also reading it? You know, and I think in your video it looked pretty nicely, but how easily was it to be grasped by the spectators?
Actually, it wasn't really easy for them to operate the entire application. Especially the entire HoloLens application had serious issues in handling the application. We had to implement, for example, a specific clicker instead of using the blooming gestures and so on, because none of the users were familiar with the technology already. And therefore, there were a lot of issues in handling the HoloLens application. And to be honest, that was one of our main limitations, that none of our users were already aware and familiar with handling the technology itself. And therefore, the HoloLens application itself raised a lot of novelty and honeypot effects and so on with regard to the hardware itself instead of our application itself. Yeah.
Okay, and then also as a comment, so you had salespeople looking at it. Well, a natural response, I would say yes, of course, they would always claim they do it much better. That was at least not so surprising to me. But the question for me was, and the other user was saying, and it should have been by glasses in this one of these big places where you can buy them. So my question would be, do you rather consider it pre-sales or post-sales? So is it something, once I bought it, it is more something I can explore my wonderful device at home and maybe recap technical details rather than pre-sales?
The technology was developed for pre-sales settings because usually when you go into a big retail store, you have no idea why a vacuum cleaner costs, for example, $50 and the other one costs $300, except of maybe you know a well-known brand. But there are a lot of products that fall in between these price ranges. And one of the issues for the actual manufacturers is how can we present our actual innovations and why a product costs that much to the potential customers. And with the augmented reality application, we try to ease the way for the customers to get an impression about the unique selling propositions. And therefore, it's definitely pre-sales in our setting, at least.
Okay, so a question that Jürgen Ziegler had, since the innovative parts were removed spatially from the vacuum cleaner to explain them, would a set of videos achieve the same effect or even better because of a better graphical quality?
It could. We haven't evaluated it, but one of our main reasons for having an augmented reality application was that a vacuum cleaner has a lot of physical artifacts, and if you touch it, you get an impression about how it feels and so on, and therefore we used augmented reality. But we haven't evaluated so far whether just video presentations could have a similar effect. But that's a good idea, of course, for future work.
And for me personally, also given that you on one side were using the sound to visualize the technology, on the other hand, that could have been annoying as well. So what about using sound in an interactive exploration of a tool? Was it supportive or was it rather the contrary?
It was supportive in that case. We just used the sound of the engine as one example, and it was perceived very well because a lot of people assume that the louder a vacuum cleaner is, the more efficiently and the more power it has. That's not completely true, but at least the sales consultant told us that that's the assumption of a lot of potential customers.
Okay, and a final tiny question. You have selected, and you may forgive me the question, you have selected 6 housewives, whatever this exactly is.
I know that it will make you raise some issues.
My question would be, it's fine for me, but my question would be, did you do a market analysis on who is actually buying the vacuum cleaner? So in a household where there's maybe 2 individuals, and there would be a female and a male, is there actually a market research on who buys it?
We haven't done a market research. What we did is we had conversations with the sales consultants, and they told us that a lot of housewives usually buy vacuum cleaners.
Okay. Thank you.
You're welcome.
Yeah, maybe one last question from my side. I like the idea with the dog, with this virtual dog, but I always have problems with the HoloLens because of the small field of view. So what do you do to find the dog, to find a vacuum cleaner? They're maybe on different locations with this small field of view of the HoloLens. Did you implement some features there?
Yeah, the vacuum cleaner was, of course, the physical vacuum cleaner, which we enhanced through augmented reality. So it was the physical artifact. And we located the dog very close to the physical vacuum cleaner. And therefore, usually the users found the dog very easily.
Okay.
And we used the Vuforia framework for all the positioning stuff.
Okay. Thank you.
Thank you, Thomas.
You're welcome.
Okay. I don't see more questions in the YouTube chat. So we should come to our last talk for today. It's a short paper. It's from Anne Elsässer. She will present a paper, and the title is Horst, the Teaching Frog, Learning the Anatomy of Frog Using Tangible AR.
Through anatomy education, children can understand how bodies of different life forms function. In the past, frogs were dissected for this purpose in biology lessons. Nowadays, different apps can simulate these dissections to avoid unnecessary animal suffering and death. These applications lack a spatial and direct visualization, as well as the haptic component traditional dissections possess. In contrast, our application, Horst the Teaching Frog, uses tangible, augmented reality to increase the learner's motivation, task performance, and the app's intuitive use. The Learning app is based on a visually realistic plush frog containing removable markers. Learners can dissect the frog by opening a zipper at the frog's belly to reveal markers representing the organs. Our smartphone app can detect these markers and replace them with 3D models of the organs. By extracting individual organs, learners can inspect them up close. The learner can then place the organ next to a magnifying lens marker to view additional details. The different features of the app are oriented on findings from established learning theories. Learners can choose between 2 dissection modes. The free mode allows the learner to freely examine the frog and its organs without providing any guidance. This should enable learners to experience learning situations in a self-directed and self-organized way as recommended from a constructivist perspective. The assisted mode guides the learner through the dissection step by step and provides additional information concerning the appearance and position of the organs. This fulfills the standards of a cognitivistic learning approach. The behavioristic learning approach is reflected by including a quiz and by putting principles of gamification into practice. The quiz allows learners to check their knowledge with a multiple choice test about the provided learning content. After each answer, the learner gets immediate audiovisual feedback on the correctness of his answer. If a question is answered incorrectly, it is put back into the question pool. As soon as all questions have been answered correctly, the user receives overall feedback and, depending on performance, a virtual medal. Furthermore, the app includes a point system, achievements, and a cross-user high score as gamification elements. Achievements are awarded in form of stickers if the learner completes certain predefined challenges. So far, a validation of Horst the Teaching Frog's effectiveness is still pending, but we are preparing to investigate the system's usability, cognitive load, and its effect on learning motivation and learning effectiveness. We intend to compare Horst the Teaching Frog to a traditional schoolbook-based approach and an app without AR or tangible functionality. Additionally, we intend to improve the system itself by optimizing the shape and appearance of the markers and by including parts of the plush frog itself as markers.
Yeah, thanks for this nice presentation. Yeah, I have a first question. Do you always also thought about the VR application? I think there's some echo here somewhere. Yeah, thank you. You need to mute your mic. Okay. Anne, can you just mute your mic because we have a strong echo? Okay, good, thank you. My first question is, you built this AR application. Did you also think about a VR application? And I think in VR you can do some additional things. For example, you can scale the organs and walk through it, which also maybe increase the learning effect to see vessels in a larger size. Why did you select AR and not VR?
We mainly picked AR since we worked with students which thought strongly on employing it in a teaching environment and basically in the short-term future. So they said they could employ a plush frog easily into the learning environment because the pupils can use their phones themselves during class. And maybe at home doing like a homework with, well, maybe a plush frog. So because of their feedback, we decided that an AR application would be more desirable.
Mm-hmm. Okay, thank you. And did you also think about multi-user interaction? So interacting together with a teacher and multiple pupils?
Yes, we thought about that, but it is not yet implemented.
Sure.
We thought about a process of having multiple pupils operating smartphones and receiving different information in the plush frog, like a skeleton or how the organs interact with each other, so that they had to communicate with each other and have a combined task of finding out how the frog works internally.
So you said that you also want to evaluate your approach in the future. I mean, this is a short paper, of course. You want to do something in the next step. And you saw in the session that a lot of people also did this and were not really successful in convincing their augmented reality application to be the best. So often the augmented reality application was not the best compared, for example, to a paper-based approach or to a personal trainer. So what do you want to do to make your AR approach the best?
So at this moment, we are planning 2 user studies. The first user study is to find out if the usability of the tangible AR app is as good as a normal AR app or as a normal graphical user interface based app. And in this process, we also want to find out if the users have any suggestions for making our app better. And the second user study will investigate the effect of the app on the learning performance. We want to make these user studies with 6th grade students. So we want to involve the people for which we are making the app. We know that there might be a novelty effect regarding AR, but we are hoping that the tangible component does have a effect that is also better than AR, since the markers can be looked at in multiple views, and that might be helpful for viewing 3D objects.
Thank you. Okay.
In the YouTube channel, there's a question on the level of indirection. So the question would be, why didn't you not overlay an existing model of a frog? So here you created an additional layer. So Jürgen Ziegler says this markers introduce an additional level of indirectness. And why did you not just sort of overlay it on a picture or on a model of a frog?
I think I'm going to answer this one. Of course, it is possible to overlay a real frog over our plush frog, but we intend to use we intended for a tangible use, because from the view of tangible user interfaces, we believe that the usability in general is better, because at least 6th grade students may not have too much knowledge about, for example, AR interaction. So they have a more or less low-tech possibility to interact with the frog itself. And we thought that reducing the amount of AR content to a good minimum would be the best way to do that. And yeah, so
I think it was also a question, if I sort of take one of your markers and I have a look at the image, it is not located where it would be in a real frog. I think that was the question. So I'm for inspection on the positive side. I'm introducing a level of indirection, and that was the question. Why did you go in favor of this one?
Yes, we actually tried to place the organs as good as possible at the location where they would be in a real frog's belly. Of course, at the moment it is missing many parts, like the skeleton, which would like obscure the view on some organs, not skeleton, but okay. And based on our research for the frog we used, I don't know the English word, but in German it's an Ochsenfrosch, I think. The organ placement and look should be as is in a real frog.
We are also preparing to make the fiducial markers and also the organs more realistic. We are working on this currently.
Okay, thanks, great.
Yeah, but
your mic is off. Yeah, okay, now it's on. Okay.
Yeah, but that the author, so like the audience is still not kind of fully answered this question. So a model would make sense. Quasi, is the cute look of the plush frog on purpose, or would it be a realistic model better? I think it's still on this kind of how much am I? It's like a toy, and how much it should be a realistic thing. So did you maybe discuss this with teachers? You repeatedly said it's maybe also for 6th grade. Any reasons for deciding for this cute thing in favor of a real, maybe not so nice looking real frog?
So a plush frog has an affordance character to the pupils because it's more like I want to play with it, not more than I have to learn something. We are hoping that the children will see the frog more than a curious thing rather than a learning material.
Okay, that's a good point. Thank you very much.
Okay. There are no further questions. That means that we are done. Yeah, the session will be closed soon.
Exactly. So
yeah, we had really nice talks. Thanks to all the speakers. It was a pleasure. Yeah, hope to see you on the MOOC conference and then tomorrow. Yeah, in the closing session, for example, for the invited talk. But there are also other nice workshops tomorrow. Yeah.
Thanks everyone for joining. I think we had a nice audience also on YouTube. Thank you for your questions and tuning in this virtual AR session.
Thank you. Bye-bye.
Bye-bye.